Welcome back. In this session, we will talk about anaerobic digestion technologies. At the end of the session, you should be able to know how to distinguish different digester types, be familiar with the scales in which AD can be implemented, and know what can be done with biogas. Let's start with the types of digester that can be used. The first way to distinguish between digesters is to look at the total solids content inside it. Here we distinguish between two main types: wet and dry digester. Wet digesters have a total solids content of about 4 to 15% TS, whereas dry digestion systems have ATS content of about 20 to 40%. Slurries or manures, such as pig manure in the first picture, have ATS value in the range of wet digestion. Agricultural feedstock, or the organic fraction of municipal solid waste, have ATS content in the range of dry digestion. We can also differentiate digesters in how the solids are fed into the digester. Here, the two main types are either continuous or batch feeding mode. In continuous mode, we constantly feed feedstock material into the digester. And at the same time, the digestate leaves the digester. As an example, here is a balloon-type digester, where we can feed a certain amount of waste, around 10 kilograms per day, into the digester, and an almost same amount of digestate comes out at the outlet per day. This balloon digester also represents a wet digestion system. In batch mode, we fully feed the digester once, close it, and let the AD process happen for a certain time. Once the AD process is completely done, we open the digester, take out all digestate, and start again. As an example, here is a container-like digester system, which is also a dry digestion system. We can also distinguish digesters in terms of their internal operating temperature. The two main temperature ranges are mesophilic and thermophilic. Mesophilic digestion takes place at temperatures of around 30 to 35 degrees, whereas thermophilic digestion is around 50 to 55 degrees. Thermophilic digestion has a higher rate compared to mesophilic digestion. However, operating digester at thermophilic temperatures also means that the digester must be heated, well insulated, and controlled carefully. Thermophilic digestion might bring the advantage of increased biogas yields, but will also increase the complexity of the system and its operation. And finally, we can differentiate digesters by their number of stages. We have two options. Either the digestion system is operated in a single-stage mode, where only one digestion tank is installed, or we have multiple stages. This means several digesters, mostly two, are installed in series. The digestate from the first stage digester serves as feedstock for the second digester. In the image above, we can see a one-stage digester at a farm, and at the bottom a larger biogas installation, with a multi-stage system. Sometimes multi-stage systems are operated at various temperatures. The first digester can be thermophilic, and the second digester mesophilic. If we want to design digesters, there are some important parameters to keep in mind. We would like to show some of them now. First, the feedstock quality plays an important role. As we have seen, depending on the total solids content we want in our digester, we can either have a wet or dry digestion system. The decision of designing a wet or dry system can be influenced by the quality of most of our feedstock, meaning its TS content. Additionally, there is an important parameter, called the carbon-to-nitrogen ratio. This ratio determines how many nutrients, meaning nitrogen, compared to carbon are present in the feedstock. This is important for the microorganisms in the digester. If not enough nutrients are present, they cannot function properly. The ideal CN ratio for AD is in the range of 20 to 1 to 30 to 1. Therefore, in the design phase of our AD system, we need to have feedstock material within this range. Otherwise, we might need to add other materials to increase or decrease the nutrient content. The next important design parameter for AD systems is the quantity of feedstock that is available every day, for example 10 tons of organic waste a day. This quantity needs to be treated every day. Together with the feedstock quantity, we also need to establish the hydraulic retention time, HRT, for our digester. We can see in this table various HRTs for different types. Commonly, an HRT of 20 days is used. With the quantity of feedstock to be treated every day, and the chosen HRT, we can calculate the needed digester volume. We simply need to multiply the HRT with the feedstock quantity. For example, with 10 tons of organic waste per day, and an HRT of 20 days, we need a digester with approximately 200 cubic meters. Next, it is important to choose a temperature range that we want our digester to operate in. If we operate the digester in mesophilic conditions, only little heating might be required, if located in a warm climate. However, if a thermophilic temperature is chosen, additional heating and an ideal mixing of the digestate are essential. A well-mixed digester will make sure that no pockets, with lower temperatures, are present in our digester, and that it operates efficiently. Additional process equipment and control will be needed for thermophilic digestion. Thus, choosing the temperature range in the design phase is important for the application of the AD system. One last important design parameter we would like to show you is the biogas yield estimation. Based on BMP tests, we understand how much biogas can potentially be produced per kilogram Vs fed into the digester. Together with feedstock quantity, we can estimate the total biogas production per day. This will determine the equipment type and size for the use of the biogas. A wrong estimation and inadequate equipment for the biogas line might not work optimally. Now that we have covered some important design parameters, let's look into process parameters. Those are parameters that are important to monitor when we have already installed an operational AD system to ensure a well-functioning digestion process. We first need to monitor the so-called organic loading rate, OLR. The OLR shows us how many kilogram of Vs we feed into the digester per cubic meter digester on a daily basis. The OLR is mostly in the range of 1.6 to 6.4 kilograms Vs per cubic meter per day. Ideally, a digester shall be fed as regularly as possible. The OLR can indicate if we are over or under feeding the digester, in comparison to the design value. Overfeeding would have an overloading of the digester as consequence, which might cause the digestion process to fail. In worst cases, the digester needs to be restarted if it can't remediate. Next is the Vs reduction rate. This value tells us the performance of the digester in terms of Vs reduction, meaning the Vs concentration after the digestion compared to the content before in the feedstock. It is calculated by dividing the Vs content of the output over the Vs content of the input times 100. Depending on the feedstock, the Vs reduction can be in the range of 50 to 90%. Another important process parameter is the volatile fatty acids concentration, VFAs. Do you remember in which phase of the digestion process the VFAs are formed? It is in the acidogenesis phase. The VFA is a parameter that can be easily measured on site and gives us a good indication about the digestion process itself. The ideal VFA concentration for mesophilic digester, for example, is in the range of 50 to 300 mg per liter. If the VFA concentration rises above 300, the digester could become acidic, which might lead to a failure of the process. Overloading could be one cause for too high VFAs. The temperature is also an important process parameter. Ideally, we have an online measurement of the digestate temperature to make sure that it is as constant as possible and within the designed range of mesophilic or thermophilic conditions. Otherwise, spot measurements of the temperature with sampling valves are also possible. A temperature profile across the digester can help us determine if the digester is well mixed. Varying temperatures along the digester profile tells us that the content is not mixed properly, and we might need to investigate the issue. Finally, we would like to also mention pH, as one of the important process parameters. The ideal pH range for AD is in the range of 6 to 8. A pH lower than 6 or higher than 8 is restrictive and somewhat toxic to the methane-forming bacteria, and will cause the digestion process to fail. A pH below 6 is linked to a too high production of VFAs. So far, we have seen the various types of digester, and some of the important design and process parameters. Let's now see at what scale anaerobic digestion is applied. Here we can see that we have a wide range of application, from small to medium and large-scale systems. On a small scale, we have digesters that are installed for single households, and with digester volumes of 1 to 3 cubic meters, for example. In the medium range, we deal with digester systems for farms, with volumes of several hundred cubic meters, or systems for small communities. At the other end of the spectrum, we deal with large-scale, or industrial-scale systems, where we have several digester vessels, reaching several thousand cubic meters each. These systems treat organic material from several farms in the area, the organic fraction of municipal solid waste in larger cities, and so on. Depending on the scale of the digester, and the amount of organic waste treated, we also produce a certain amount of biogas. Let's see what we can do with the biogas at various scales. At household level, or small scale, we produce only few cubic meters of biogas per day. The main use of biogas is for cooking. The biogas is burned in modified gas stoves, for that purpose. The produced biogas lasts on average for about 2 to 4 hours of cooking per day. On farm-scale systems, we already produce enough biogas to run a specialized engine with a generator producing electricity. If we also make use of the heat generated during the combustion of the biogas in the engine, we can use most of the energy contained in the biogas. At large-scale systems, the size of the biogas engine increases to produce more electricity and heat. The heat is often used partially to heat the digesters, especially if they are operated under thermophilic conditions. At industrial-scale systems, we can also find systems that don't burn the biogas in engines, but split the methane fraction out of the biogas, using specialized membranes. We then have almost pure methane, which is basically natural gas. The biomethane is either injected into a natural gas grid, or bottled and sold. As byproduct, we get carbon dioxide, which can also be used by other industries. Now we have seen what can be done with the biogas produced at various scales. To give you a better feeling of the time one can cook, or how much electricity can be produced, let's have a look at some numbers. Let's assume we have about 10 kilograms of wet waste, with ATS of 15% and VS of 80%. Laboratory BMP tests have shown that we can expect a methane yield of about 600 liters per kilogram VS from our wet waste. Now let's imagine we have a small household digester, and we want to use the biogas for cooking. For every 10 kilograms of wet waste, we can produce about 1 cubic meter of biogas, which contains about 6 kilowatt-hours energy. If we burn this in a standard gas burner with 3 kilowatts power, we can cook for about 2 hours. Let's see what we can do with the biogas, assuming that we have a medium or large-scale installation. We can run, for example, a combined heat and power plant, CHP, which generates electricity and captures the heat. In modern CHPs, we can achieve up to 40% electrical efficiency, thus generating about 2.4 kilowatt-hours electrical energy for every cubic meter of biogas. The heat recovery efficiency is up to 50%, generating about 3.0 kilowatt-hours of heat energy for every cubic meter of biogas. In large systems, we can also split the methane and CO2 fraction in the biogas with modern membrane systems. The gas recovery efficiency could be up to 99.5%. We can thus extract about 0.595 cubic meters of methane and 0.395 cubic meters of CO2 per cubic meter of biogas. As we can see, biogas is very versatile and has a lot of potential uses, which makes anaerobic digestion such an interesting technology. This is it for this session. Let's summarize our learnings. We learned to distinguish digester types, according to 4 criteria categories. We learned about important design and process parameters for AD systems. We had a look at the scale at which digesters can be implemented. And finally, we have seen what the produced biogas can be used for at different scales, and some biogas key conversion figures. Thank you for listening. See you in the next session.